Welcome to our first monthly webinar series on machine learning based prediction of malaria. We are delighted to have you join us today for this activity. A big thank you for taking time out of your day to be with us. My name is Dennis Mureithi. I'm an associate professor, at Chuka University, Kenya, and a member of Machine Learning Network Group. Machine Learning Network Group is an online community of individuals, researchers, data analysts, modelers, and professionals who are interested in the field of machine learning. The aim of this group is to push the boundaries of machine learning by developing new algorithms, models, and applications in malaria modeling. This initiative also complements work done by AMMNet. AMMNet stands for Applied Malaria Modeling Network. And as you know, AMMNet is a global community of malaria modelers, data analysts, and partners who develop and apply and use quantitative tools to inform decision making and operations in malaria epidemic countries. AMMNet is a collaborative initiative focused on utilizing mathematical modeling and computational techniques to study and combat malaria. It brings together researchers and experts from various disciplines to develop models that can inform strategies for malaria control and elimination. AMMNet aims to improve our understanding of malaria transmission dynamics, predict the impact of interventions, and contribute to the global efforts to reduce malaria burden worldwide. For more details on AMMNet activities and opportunity, check on AMMNet's website. Today, webinar will focus on exploring various machine learning models for malaria prediction using R software. In our program, we have 5 items. One is introduction and welcoming the participants. Once again, you are most welcome for this activity. 2, we are going to have the webinar lecture session, which will take about 50 to 1 hour minutes. The third item is hands-on session, which will take about 30 minutes. We will also have questions and answer session for about 20 to 30 minutes. And finally, the closing remarks. We are confident you will walk away with valuable insights on today's topic. Our lecture today will be delivered by our group leader, Professor Awe. So kindly allow me to give you a short introduction about Professor. Professor Olawale Awe is a distinguished Nigerian statistician. Kindly mute so that we can move together. Professor Olawale is a distinguished Nigerian statistician, professor, and data analyst. He serves as Vice President of Global Statistical Engagement for RISA 2020 Global Network and a council member of International Statistical Institute. Professor has led numerous capacity building workshops aimed at enhancing the skills of young researchers in Africa. This initiative significantly advanced their capabilities and fostered collaborative engagement with the research community. Beyond his organizational roles, Professor is actively involved in research and outreach activities that promote the advancement of data science and its practical applications worldwide. He has published over 100 interdisciplinary scholarly articles in reputable journals Currently, Professor Awe is a research professor and team leader at the Statistical Learning Laboratory of the Federal University of Bahia in Brazil. So that is a bio sketch of our presenter today. I now take this opportunity to ask Professor to take us through the next session. And as we welcome the Professor, we will have question and answer session. So keep your questions till the end of the lecture. Professor, you are welcome. Kindly take over the session.
Thank you so much, Professor Dennis. Thank you, distinguished ladies and gentlemen, for joining us today. I would like to quickly share my screen as we begin this first webinar series. It promises to be great, and we're going to learn together various methods of applying machine learning to health data. So today we are considering a very important subject, very important activity that can be useful for health researchers in our group. And we're going to look at various machine learning models, ways of building various machine learning models for prediction of health data. But particularly, we're going to be considering malaria today. Malaria So kindly pay attention as we move on. So we are going to use R today. So the first thing in building your models is to, first of all, of course, you must have installed your R and R Studio. So in your R, you have your libraries. First of all, you load your libraries. We have different libraries here. We have the Caret, which is the major library we're going to use today to build or to train our machine learning algorithms. Then there is a Psych library, which is used for description of data. I have ggplot, which is well known for data visualization. We have Caret ensembles, which enables the creation of ensemble models. Tidyverse for various data manipulation. The ML bench for benchmarking machine learning models. If you like, you can put a flex table in case you want to represent a particular data set in tabular form. Then ML tools for hyperparameter tuning. Then TikTok for determining the time taken for a model or algorithm to run or to converge. Then we have the rows, which is run for random oversampling. Then we have Smooth family, which is also used for oversampling data to undo data imbalance. And then we have the ROCR for handling, for plotting your area under the curve. Now, by way of introduction, machine learning is one of the most popular fields or most popular methods in science, because machine learning comprises of, or it constitutes its use for handling most of the problems in data science, in health data science. So machine learning is a very powerful subfield of artificial intelligence that focuses on the development of algorithms and statistical models that enables the computer to to perform without being explicitly programmed. Now, it works in such a way that it learns from the data in order to improve the performance of the model over time. So the machine learning models are black box models that you only need to train using your data. They are highly data-driven. Now, we have three major types of machine learning. We have the supervised machine learning, we have the unsupervised machine learning, we have reinforcement learning. Now, the first part is the one we are considering today. The supervised machine learning works with data that has outcome and features, or output and input, which means that if you have a data set whereby you want to predict something, maybe you want to predict either the next set of patients, for instance, in health data science, maybe you want to predict whether the next set of patients will have a disease or not. You can use predictive type of machine learning, which is the supervised machine learning. It has the outcome that we want to predict and the feature variables that we will use to predict the outcome. You know, you must have collected some data on the patients. Maybe you have data on the symptoms of the patient, and you now use it to predict or diagnose the outcome. So that is predictive analytics. That is supervised machine learning. But if essentially you are just clustering, I mean, you just want to find out the various clusters, then you are talking about unsupervised machine learning. So supervised machine learning is essentially what we are considering today. And I hope that you enjoy this as we go along. Now, the data set we are considering is a data that was collected from an hospital in Nigeria, malaria data. You know, the data borders on diagnosing either patients who have severe or not severe malaria based on some symptoms that they display or that they present. So I'm going to share the data with you. The data is publicly available. It has even been published in Data in Brief. Now, here is the data. The first thing you need to do, want to apply machine learning after loading your libraries, is to load your data sets in R. This is how to. This is how to load your data. So this is the data that we are using. Now, the malaria data is in my working directory. It's assumed that it is in my folder, which is my working directory. So I just simply need to name it here and just run it. I'll just run it, and then I will check the dimension. dimension of this data, it means I have 337 observations or patients with 18 features. So that means one of them is the response. So how many features are left? Left with 17 features. And actually, here is the data. Mostly you can see they are categorical. You can see 0, 1, 0, 1, whether the patient presents with such a symptom or not. Right. Now, the only numerical variable here is age. And as you can see, the age here ranges from 3, look at it, from even infants to adolescents and so on. So the age range is so different. I'm going to plot the age so that you'll see it later. If you like, you can plot the age. Now let's check the head of the data just to see the few first rows of the data. Then look at the names, the variables in the data set. So we have age, we have the symptoms now, the characteristics of the patients, whether this is the gender, the sex, this is fever, whether the patient comes with fever, so that we can diagnose, we can use machine learning to predict whether it's severe malaria or not severe malaria. Look at cold, whether it has rigor, fatigue, headache, bitter tongue, whether it's having anemia, or whether the patient is having convulsion, diarrhea, vomiting, jaundice, Coca-Cola urine, hypoglycemia, obstruction, which is maybe almost fainting, then hyperglycemia, then severe malaria. This is the response variable. This is the output. This is the output. All the other ones are the features that we want to use to predict this output. Right. I'm going to attach this data set. I'm going to attach it so that it can easily recognize each feature. Now, let's summarize each feature. Look at it. We can see the various features being summarized. Now, the essence of summarizing is to see whether there are no missing values. Also, you can see there's no missing value in this data set. So bear in mind that all that we are doing here is assuming that you have pre-processed your data. You have actually cleaned your missing, you have dealt with your missing data. You have transformed your data as you want it, and the data is well set such that there are no issues. So that is assuming that you have a processed data. Maybe later on, we can have another webinar on handling your data or pre-processing your data. But here, the data we are working with here is assuming that the whole data is well processed already. Now, you can use this option in training if you have missing data. This Caret package that we're going to use here can also undo missing data alongside. So it's a very powerful package. I'm going to introduce you to a Caret package for those who do not know about it. I'm going to introduce it to you shortly. Now, let's first of all rename the classes of our response variable, output variable. You know, remember it was 0, 1, just 0, 1. But we want to give it a specific name. We want how to recognize the names. So I use this code to do that. This is the severe malaria. Don't mind the spelling of malaria here. This is the severe malaria. And now we are saying when it is 0, make it not severe. When it is 1, it is severe. That is what the data represents. Now let's plot it. Let's plot it. I'm plotting it with this particular code. So I just say plot factor. This factor is just to make it categorical, to ensure that it is categorical data. Now, the names, I gave it names, not severe and severe. Look at it here. Then I label the x-axis. I give the y-axis a limit, and I label the axis. The y-axis is responded, the patients, and the x-axis is the type of malaria detected or malaria diagnosis. So not severe and severe. As you can see, you will see that severe is quite lower, quite smaller than the not severe, which is actually a case of imbalanced data. This can cause problem in our modeling, but we are going to see how we can undo that later on. But let's first of all build the models. Let's see how the models will behave, how the models will predict the cases first of all, before we start handling missing data. If you like, you can even use ggplot. Can uncheck this one. I'm going to share this code with you. You can use it for your publications and papers. You can see this is what ggplot gave me. You can see it's even showing it better. You can see the wide margin. You can see between the not severe and the severe, right? So that is a very typical case of imbalanced data. But then let's hang on that, and let's continue building the models first. So we are getting ready to start building our models. Now, one major characteristic of supervised machine learning is that you must divide your data into 2 or 3 parts so that the algorithms can learn well on your data. You must be able to divide the data into 2 or 3 aspects. For now, we're going to divide into 2 major parts. Maybe in our next subsequent webinars, we'll show you how to divide into 3 parts. Now, the 2 parts we are dividing the data into, they call it data partition in machine learning. We divide into training and test sets. Train and test sets. Now, the train set will take the larger proportion. Here, I'm using 70% train set and then 30% test set. Take, for instance, you are a student. The time you use to train, to learn your studies is much more than the period of test or the period of examination, isn't it? So that is how it is. Usually, the train set should be bigger, larger than the test sets. So that is what is going on here. The machine learning algorithm will train with this 70% of the data to be able to use 30% of data to test the performance of the model by computing what is called the confusion matrix. Confusion matrix is just essentially a matrix that contains how the machine learning algorithm is performing. So we need to separate the data into train and test. So this is how it is being done, train and test. So what I'm just saying here is just a simple code. Let's sample my data into 2 and then give me the first proportion to be 70, the second proportion of the data to be 30%. Then call the first one train, call the second one test. Now let me check the dimension of the train and set. Look at it, it has separated it. Still the same number of columns, but it has separated the 337 that we had earlier into 2, 2, 3, and 1, 1, 4. Now let's go ahead and we are ready to go. We're about getting ready to go. But before we go on, we are going to look at Caret, a package called Caret. Like I told you, it's a powerful package. It's a powerful machine learning package. Yes, package, which is very Now, it was developed by in 2021 and it's very new. So the Caret is a short name for classification and regression.
Hello, Prof. Kindly, participants are requested to mute your gadgets, please. That will be on the same side. Kindly.
And models for classification and regression. What is classification? Classification means that you have a categorical output variable. When you have a categorical output variable, then you are talking about classification. But when you have a continuous output variable, then you're talking of regression. And there are some models that are specifically built for classification, whereas some models are specifically built for regression purpose. Now, this Caret package is very, very useful for machine learning and for researchers, like I told you. In fact, it contains over 200 different machine learning models. 200, more than 200, almost 300 machine learning models on which you can choose from. Now, don't worry, we do not expect you to know all the 200, but I'm going to show you how you can go about it. So it means that using this Caret, if you have good data sets, using this Caret package, you can begin to try several models. You can begin to try several models. And then you'll see that it is very, very useful. Now, let's see how we can build our models. But before that, let me show you Caret. Now, let's see the model info. You can run this code to get the model info and then to have the models. Look at all the models here. Look at them. Look at them. 238 so far. 239 rather so far. Look at them. Look at them. Look at them. So many. So it means that on a particular data set, you can try all these models. If you have just 2 or 3 data sets, you can try all these models on them, and some of them can be publishable, right? So look at all the models. All the models. We have other, we have bridge, we have a lot of models. Can you see them? Now, let's see how we can use some of them. Now, today, I'm just going to show you how to use 10 of them. I'm just going to build just 10 of these models for you. So we're going to consider support vector machine, random forest, naive Bayes, linear regression, logistic regression using the GLM. We're going to do k-nearest neighbor, and we're going to do linear discriminant analysis. We're going to do neural network. We're going to do linear vector quantization. We're going to do bagging and boosting. The last two there, they are ensemble methods, which is a combination of several models. Now we're going to see whether these ensemble methods will be better than the other models. By the way, the random forest is also an ensemble method because it operates using the system of bootstraps aggregation. Now, let's begin by preparing our training scheme. You don't stop there. You don't just build your model. You have to prepare your training scheme. You have to use something called cross-validation. What that means is that you divide the data into several parts again. It has an inbuilt mechanism that divides the data into several parts again and repeats severally, so that at the end of the day, the algorithm that will be built has been tested severally, and it will be highly accurate. So the train control is a function here. And the method we are using is repeated cross-validation with 10-fold repeated cross-validation with 5 repeats. So it means we have 50 in all. We'll revalidate, with each model. And that means we have a very high level of prediction. We have really tested the model. We have really validated the model such that if you like, you can repeat the number of, you can increase the number of repeats, or you can even increase the number to see whether your model will produce higher accuracy or higher sensitivity and all that. Now, we are going to begin, having set our training scheme, we're going to begin by training our models. So we have our models here, train our machine learning models. Remember, I said we're going to train 10 machine learning models today out of all these 239 or 39 models that we have here. Now, the first one we are looking at is support vector machine. So the way the Caret works is that you just give a name of the model, right? Give it a name, and this is the object that stores the model. And then the train, this function train is the major function in Caret. Used to train your model, used to build your model. Then what you have here is y depending on x. So it's an input-output mapping, output-input mapping, such that the Y is the response variable, and X is the input or the features that we have in the data. If you just put a dot here, look at this tilde sign is the mapping sign. This tilde saying Y is a function of X. Use this X to predict Y. Whatever you put here is what will be predicted. Actually, the name of the response variable is severe malaria. Don't mind this spelling here. This is how it is in the Excel. I mean, when it was collected. So we can't change it here. If you change it, it won't run. Now, the dot here signify all the other variables. If you like, you can just give specific name. If you wanted to use just 5 variables, you can just label them. You can just name them and use plus. Just name them here and use plus. Put them here. It's the same way they were spelled, and put plus. Now, you see data equals train. We are using the train data. You remember we splitted the data into 2. We're using the train data to run the original model, and the method is support vector radius. Actually, it is not a linear model. So we are using support vector radius, the non-linear kernel of support vector. Then the train control that has been specified before is what we are also putting here. So if you like, you can take in more things. You can do hyperparameter tuning here. In subsequent lectures, I will show you how to do hyperparameter tuning. You can even fill in missing values here. You can do preprocessing, data preprocessing here. So this Caret is so powerful that in just 1 or 2 or 3 lines of code, it has done a lot for your model. And not minding the way your model, your data was before, whether it contained missing values, whether it contains some outliers or whatever. It will just preprocess everything. I will show you how to do that in subsequent lectures. Now, let's run this. Now, it didn't run because I've not run this. You have to run it one after the other. Now, what is this tick doing? This tick is getting from the TikTok package. If you want to check the time taken for each model to run, you have to load the TikTok library for the time taken for a model to run. Now, let's go there. If you want it, you can put it there. So here is how it works. Before the beginning of the model, you have to put tick here. You put tick here. First of all, we set seed so that anytime we rerun the model, it will show the same result. It will display the same result. Somebody complained to me sometimes ago that, oh, I'm running my model, and it kept on giving me different accuracies, different results. Oh, this is how to handle the situation. Just set your seed. You can put any number in here, but be consistent. Set your seed, and then if you want to record the time taken for each model to run, if you're interested in reporting that, this is another result you can report in your publication. Some journals or some reviewers want to know, so that they'll be able to judge which model is faster, so that you can even, especially in the industry, you can project it to them and say, oh, this model is good in terms of accuracy, sensitivity, in terms of fastness. This model is the best. You can also discuss in that line. So you put this tick here, you run the model. Now you can see it run. When I've run the control, then the talk is there. And then let's call out what we have already done. This is the SVM model. Don't forget, Now it's recording our accuracy and kappa. I'm going to tell you more about kappa later. Then let's now use the test data to validate the model, to predict, to validate the model. I'm taking time on this first one because all the subsequent ones will follow the same pattern I'm going to show you. It's so simple, so straightforward. You're going to follow the same pattern. And then you use the test. What is happening here is that we are trying to judge how the algorithm will behave on new data sets. People that are close to you, they are likely to predict you in the same way, favorably. But let's bring some 3 or 4 random people that do not know you well. Maybe they just met you 1 or 2 times. They don't even know you. Some may not even know you at all. Let them just assess you at first glance and see what they will say. Then, with the combination of all these assessments, we are likely to believe the model better. That is essentially what is happening here. So let's do that. So now, the test data is this. Then now it's telling me that subscript out of 1, probably because I did not run the test here. Let me run the test here again. Because my previous model that I ran, I used the same test to indicate that data. So let me run it again. Okay, so make sure that your data is well labeled. Okay, positive is severe. Positive here, what did I name it with here? Okay. I named it with severe here. Severe, okay. Now it's showing me the accuracy and the kappa. Now it has run. So in case you come across any error, just don't bother. Don't be ruffled. Just go over again and take it carefully and run your data afresh. Some people, when they meet with error, they are afraid, they leave it alone and they don't go back again. You have to stay at it and run it again. Now, let's see the confusion matrix. The confusion matrix, like I said, is a matrix that enables us to judge the performance of the machine learning algorithm. Now, the machine learning, each machine learning algorithm will be judged based on some metrics, performance metrics. We call them performance metrics. How do they predict the disease? Sometimes, we have positive and negative. those who are positive with the disease, who are severely infected, and those who are not severely infected, like the case we are considering here. Those who are not severely infected and those who are severely infected. So the machine, the algorithm will predict those, sometimes it will say true positive, true negative, false negative, and false positive. The confusion matrix is a matrix for a 2x2 case. It's a matrix that shows us the number of patients that the machine, the algorithm is predicting as truly positive. What do we mean by truly positive? True positive is the number of people that they are truly severely infected, and the algorithm is predicting them such. What of true negative on the diagonal? So on the diagonal of the confusion matrix, we have true positive and true negative. On the off diagonal, we have false negative and false positive. So the false negative are the off diagonals are the errors the machine learning is making, whereas the diagonal are the correct predictions of the algorithm. Now, let me show you. Look at the matrix here. Look at the matrix here. Look at it. This one is flipped. This is true negative. True positive, and true negative, false negative, and false positive. Now, you can see that the prediction here is so low. There's nothing here in this diagonal element here. So that means this algorithm has an issue. And probably it could be because of the imbalanced nature of the data. Look at the accuracy here is somehow low. Maybe there are things we can do to improve this particular model. We are going to see as we move on. Look at the kappa. Kappa is just 0 here, which is not a good indication that the model is really, really good. It didn't even give us any precision. It didn't even give us any F1 score. F1 score is the harmonic mean of the sensitivity and precision. That's why, because precision is not applicable here, then F1 score is also not applicable, probably because it's reporting zeros here. No. Now, accuracy is the addition of the diagonal elements divided by the addition of all the elements. So in essence, this accuracy here is just 63 divided by 36 here. That's why we have this percentage, and we have 63%. Now, let's see the balance. There are other measures like balance accuracy. Balance accuracy is the average of sensitivity and specificity. Now, you can see that this model is not doing fine enough. That's one good thing about machine learning. You don't run one model and stop. You keep trying. Now, let's try with other models and see. Now, when we plot the confusion matrix, want to see it better, I use this code to plot it. You know, I remember I called it out here. Look at it here. What I just did is to do 4 plots of this table here. And then we want to do inference. Now, variable importance. We want to see the features that are more important for predicting whether the patient will have severe malaria or not severe malaria. Now, this is the picture of the variable importance. Don't mix it up with significance. It's not showing significance. There's no p-value in machine learning. We are talking about importance here. Now, age is showing as the most important variable because you remember there are infants there. So it is likely that most of the infants will be severely affected. So the age disparity is too much in this group of patients. So age is one of the, then followed by headache. It's one of the other important features for measuring either severe malaria or not, and diarrhea here, and followed by fatigue, hypoglycemia. That's what this support vector model is judging. Now let's go ahead and follow the same process to train the random forest model. Look at it the same way. Put the response variable here as a function of dots. Dots shows that if you just put dot, even if there are 1,000 variables or features in the data, it will pick all of them and put in the model. But remember what I said, if you wanted just few of them, you will just put it there. Data equals train, method equal to random forest. Just pick it, random forest. Now this model has finished running. It took just 32 seconds to run. Straight control is straight control. And then we'll run it. Then we'll go ahead and follow the same process. Then we'll plot the confusion matrix and then the variable importance is still saying that age is the best. So it's becoming more believable, but we don't stop there. Let's go ahead with logistic, excuse me, regression. Now, this time around, I'm not taking the time. If you like, you can put TikTok just to measure the time it takes. Now, let's go ahead and run this. Okay. Okay, you can see this one looking like an improvement on the previous one. There we had 0 zeros. Here we have something. Now let's go. Now let me have the performance measures. Okay, look at it. This one is giving me accuracy of 58, 59%, and then it's giving me sensitivity of 11%, true positive rate of 11, which is very low, you know, to predict the positive cases, and the specificity, which is 85%, which is quite low, and all that. Then precision is 30%. Then F1 score is 16%, and balance accuracy is 60%, which is still low. What of K nearest neighbor? You follow the same process, run it, and then you can view the listing here. You can run it here, It's even lower. It's even lower. Although it's reporting something here, but this one has also reduced. So that is the reason why it is even lower. Now, look at it. This, don't forget, this is the reason. This may be because the data is imbalanced. Don't just report this result and go and publish. Do more. Now, let's see. Age, headache, almost the same thing. So that means in this data, age is very, very prominent here. I'm going to, let me even plot the age. Let me see that age variation, age distribution. Oh, look at it. It follows a linear kind of pattern. You can see from almost age 1 to you can see how it is moving. Sorry, age 3 moving to even 60, 70, putting them, the age disparity is too much here. So we may have to do something later to scale up that age to pre-process that particular data. So that is why it is showing up incessantly like that. So let's look at the neural network. This one may take a little time because it is a deep learning technique. Wait for it. We are almost wrapping up. Okay, it's showing us. Look, no sensitivity at all. Look, 63%. I'll show you what all this means later. Then let's plot the, then this time around, this one is saying fever is the most important. And followed by jaundice. Where is age? It brought age down. So who do we believe? That's why machine learning, there's no free lunch theorem. You can't just pick one model and believe. You have to try several models. You have to try several models and use several techniques to judge them. Okay. Now let's go for our naive Bayes model. Naive Bayes is also a very powerful classification model. Oh, that was fast. Okay. Now let's look at the metrics, almost the same thing with the other ones. Let's see. Oh, it came back to age again. Only neural network is different, probably because it is a deep learning model. Now let's look at linear discriminant analysis. Okay, there's something wrong here. Let me correct it. Oh, I put infected instead of severe. Okay, I'm going to correct that, and it's going to run now. And if I put R is case sensitive, if I put small s instead of big S, it won't run, okay? Now it ran. Now let me plot let me look at this again. Okay, now look at it's even also lower, all because this is imbalanced data. Now it's saying the same thing with the others. Linear vector quantization model. So the method will be LVQ. The method here is just LDA. The method here is NB, naive Bayes. Very straightforward. You just plot it, and then you can write comprehensive reports on this. Now, it's saying subscript out of bound because previously I named it as infected, but actually it is severe. So I'm going to run it again. Now it worked. Okay. I'm going to plot the geometries and showing the same thing.